Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 4th, 2025, about 6 days ago. It shows that when database systems are carefully redesigned around Linux I/O Uring, throughput can more than double, with speedups of 2.05 times and 2.31 times in key experiments, and an extra 14% boost for PostgreSQL on top of its existing I/O Uring backend. The paper is titled High Performance DBMSS with I/O Uring, When and How to Use It. And as we will see later, the implications for future high-speed data systems are quite significant. Alright, the introduction set up a big gap between fast hardware and slower software. Figure 1 now quantifies how much careful I/O Uring design can close that gap. The left buffer manager chart shows that simply swapping libaio for basic I/O Uring barely helps, rising from about 173,000 to 184,000 transactions per second. But an optimized I/O Uring design jumps to roughly 376,000. The right network shuffle chart tells the same story, where bandwidth crawls from 12 to 13 gigabytes per second with naive I/O Uring, yet a tuned design reaches about 31 gigabytes per second, more than doubling throughput. Well, Figure 3 explains how I/O Uring actually runs requests inside the kernel, which is crucial for those performance gains. The left SQ ring and right CQ ring show where requests enter and results return, connected by the main inline completion path that is fastest when I/O finishes immediately. Below, the poll set with event handlers represents true asynchronous non-blocking execution. Above, the async worker pool handles slow, blocking calls as a fallback, while the optional SQ poll thread beside the SQ ring can submit work without extra system calls. Alright, Figure 5 turns those kernel mechanics into end-to-end throughput numbers for the YCSB storage workload. The left synchronous I/O bars stay stuck around 17 to 19,000 transactions per second, whether they use POSIX calls or basic I/O Uring. The middle asynchronous region shows the real gains, where fibers, batch submission, registered buffers, pass-through, and poll modes push throughput up to about 376,000. The rightmost bar then adds a second core for submission queue polling, which finally reaches roughly 547,000 transactions per second. So, while Figure 5 showed the big end-to-end gains, Table 1 supplies the low-level numbers that explain them. The left section lists raw I/O latency, with a single read taking about 70 microseconds and a single write about 12 microseconds. The right section reports CPU cycle costs, where a transaction uses about 8,300 cycles, a single read about 10,000, and batched reads and writes around 5,400 to 5,700 cycles. These costs underpin the simple throughput model the authors derive. Alright. Figure 6 compares transactional throughput for the TPC-C workload under different buffer managers and I/O Uring optimizations. The left panel, with one warehouse mostly in memory, shows VM cache far behind, while libaio and basic I/O Uring cluster around 59,000 transactions per second and advanced options add only small gains because the workload is compute-bound. The right panel, with 100 warehouses mostly out of memory, shows VM cache collapsing to about 2,000 transactions per second, while fully tuned I/O Uring climbs to roughly 33,000, so non-blocking I/O and polling features matter most when storage dominates cost. So, while Figure 6 compared transactional storage, Figure 11 shifts to the distributed network shuffle. The figure plots per node egress bandwidth as worker threads increase, with 3 panels for 64-byte, 1024-byte, and 4096-byte tuples. In each panel, the red default curve grows slowly and stays far below the link limit. The green zero-copy send curve climbs higher, and the blue zero-copy receive curve climbs highest, especially for larger tuples, showing that removing kernel copies unlocks much more network throughput. So, while Figure 11 highlighted network gains from zero-copy, Figure 17 shows how those same ideas translate into a real PostgreSQL deployment. The 4 panels compare 1, 2, 4, and 8 workers scanning a large cold table, and each bar stacks extra I/O Uring features. Registered buffers and I/O poll give only modest speedups of around 4 to 7%. The big jump comes from SQ poll, which pushes speedups to roughly 12 to 14%, even though the file system and multi-process design still cap the benefits. So the key message is that I/O Uring is not a magic drop-in, but a powerful tool when database architectures fully embrace asynchrony, batching, and features like registered buffers, polling, and zero copy. The broader implication is that future high-speed data systems must be co-designed with the operating system. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.